In this video, we are going to talk more about modern glass bottle manufacturing factory and bottling processes. The manufacturing of glass bottles comprises a number of stages. They include crushing and mixing of raw materials, batching, melting, formation processes, annealing. The manner in which these steps are performed may be adjusted depending on the glass bottle product. How to make glass bottles step by step. Raw materials that is primarily used in the manufacture of glass bottles are sand, soda ash, limestone and cullet. These materials are mixed in a specific ratio to make soda-lime glass. Other types of glass bottles may, however, require additional inputs. For instance, dyes and chemical compounds may be added in the manufacturing process to produce colored bottles or heat-resistant borosilicate glass. Once the raw materials are gathered and prepared, they are placed in a hopper machine for mixing. The mixture is then put into batching compartments in measured portions. It is from these compartments that it is fed into the melting furnace through a conveyor belt. Batching is an important phase of glass bottle manufacturing. The mixture portions have to be accurate to ensure consistent quality. Their sizes are determined by the design and the number of bottles to be made. The melting phase takes place in a heating furnace, where the raw materials are subjected to high temperatures of about 1600 degrees centigrade. The water content evaporates and organic matter is burned off, while the remainder of the mixture melts to form molten glass. Finally, the molten glass is cooled to achieve viscosity and readiness for the formation stage. All furnaces are fully automated. Their temperature settings are controlled by engineers from an integrated control room using special software. Glass formation involves the molding of molten glass into the desired bottle shapes. First, the viscous mixture is cut into gobs of equal size, using a timed blade. The gobs fall into separate slots of an individual section machine. Each slot contains a shaping mold. The final shape is achieved by either blow and blow method or press and blow method. In the blow and blow method, compressed air is used to shape the bottle. It is blown onto the molten gob and pushes it to take the shape of the mold. This initial shape is referred to as a parison. The parison is then flipped to an upright position, reheated and injected with more air to fully define its shape. This method is used for narrow glass bottles such as beer glass bottles, wine glass bottles or soda glass bottles, . Next, annealing and conditioning processes in glass bottle manufacturing. After the rigorous process of formation, the glass bottles are allowed to cool before being moved into an annealing LENR. It is a long kiln that has controlled temperature settings. In it, the glass bottles are slowly reheated and then gradually cooled again to a temperature below the strain point of glass. Annealing is important as it minimizes the internal stresses in the glass bottles that can lead to shattering. It also ensures an even settling of the glass material. The annealing process must be controlled to ensure the consistency of material, minimize stresses, and prevent spontaneous breakage. Surface treatments are performed on the exterior of glass bottles when they are complete. They can be used for decoration, labeling, and even protection against abrasion. Some specialized equipment and know-how in performing various treatments including engraving, screen printing, spray painting, crackling, electroplating, baking, frosting, and matting. Broadly, modern glass container factories are three-part operations: the batch house, the hot end, and the cold end. The batch house handles the raw materials, the hot end handles the manufacture proper, the four-half, forming machines, and annealing ovens, and the cold end handles the product inspection and packaging equipment. Glass containers typically receive two surface coatings, one at the hot end, just before annealing, and one at the cold end just after annealing. At the hot end, a very thin layer of tin 4 oxide is applied, either using a safe organic compound or inorganic stannic chloride. Tin-based systems are not the only ones used, although the most popular. Titanium tetrachloride can also be used. In all cases, the coating renders the surface of the glass more adhesive to the cold end coating. At the cold end, a layer of typically polyethylene wax is applied via a water-based emulsion. This makes the glass slippery, protecting it from scratching and stopping containers from sticking together when they are moved on a conveyor. The resultant invisible combined coating gives a virtually unscratchable surface to the glass. Due to reduction of in-service surface damage, the coatings often are described as strengtheners. However, a more correct definition might be strength-retaining coatings. Glass containers are 100% inspected. Automatic machines, or sometimes persons, inspect every container for a variety of faults. Typical faults include small cracks in the glass called checks, and foreign inclusions called stones, which are pieces of the refractory brick lining of the melting furnace that break off and fall into the pool of molten glass, or more commonly oversized silica granules that have failed to melt and which subsequently are included in the final product. These are especially important to select out due to the fact that they can impart a destructive element to the final glass product. For example, since these materials can withstand large amounts of thermal energy, they can cause the glass product to sustain thermal shock, resulting in explosive destruction when heated. Other defects include bubbles in the glass called blisters and excessively thin walls. Another defect common in glass manufacturing is referred to as a tear in the press and blow forming. If a plunge and mold are out of alignment or heated to an incorrect temperature, the glass will stick to either item and become torn. In addition to rejecting faulty containers, inspection equipment gathers statistical information and relays it to the forming machine operators in the hot end. Computer systems collect fault information and trace it to the mold that produced the container. This is done by reading the mold number on the container, which is encoded on the container by the mold that made it. Operators carry out a range of checks manually on samples of containers, usually visual and dimensional checks. Glass container manufacture in the developed world is a mature market business. World demand for flat glass was approximately 52 million tons in 2009. The United States, Europe, and China account for 75% of demand, with China's consumption having increased from 20% in the early 1990s to 50%. Glass container manufacture is also a geographical business. The product is heavy and large in volume, and the major raw materials are generally readily available. Therefore, production facilities need to be located close to their markets. A typical glass furnace holds hundreds of tons of molten glass, and so it is simply not practical to shut it down every night, or in fact in any period short of a month. Factories therefore run 24 hours a day, 7 days a week. This means that there is little opportunity to either increase or decrease production rates by more than a few percent. New furnaces and forming machines cost tens of millions of dollars and require at least 18 months of planning. Given this fact, and the fact that there are usually more products than machine lines, products are sold from stock. The marketing/production challenge is therefore to predict demand both in the short 4 to 12-week term and over the 24 to 48-month long term. Factories are generally sized to service the requirements of a city. In developed countries there is usually a factory per 1-2 million people. A typical factory will produce 1-3 million containers a day. Despite its positioning as a mature market product, glass does enjoy a high level of consumer acceptance and is perceived as a premium quality packaging format. Glass containers are wholly recyclable, and the glass industries in many countries have a policy, sometimes required by government regulations, of maintaining a high price on color to ensure high return rates. Return rates of 95% are not uncommon in the Nordic countries, Sweden, Norway, Denmark and Finland. Return rates of less than 50% are usual in other countries. Of course, glass containers can also be reused, and in developing countries this is common. However, the environmental impact of washing containers as against remelting them is uncertain. Factors to consider here are the chemicals and fresh water used in the washing, and the fact that a single-use container can be made much lighter, using less than half the glass of a multi-use container. Also, a significant factor in the developed world's consideration of reuse are producer concerns over the risk and consequential product liability of using a component of unknown and unqualified safety. How glass containers compare to other packaging types is hard to say. Conclusive life cycle studies are yet to be produced. As with all highly concentrated industries, glassworks suffer from moderately high local environmental impacts. Compounding this is that, because they are mature market businesses, they often have been located on the same site for a long time, and this has resulted in residential encroachment. The main impacts on residential housing and cities are noise, fresh water use, water pollution, air pollution, and dust. Noise is created by the forming machines. Operated by compressed air, they can produce noise levels of up to 106 bar. How this noise is carried into the local neighborhood depends heavily on the layout of the factory. Another factor in noise production is truck movements. A typical factory will process 600 t of material a day. This means that some 600 t of raw material has to come onto the site, and the same off the site again as finished product. Water is used to cool the furnace, compressor and unused molten glass. Water use in factories varies widely. It can be as little as 1 ton water used per melted tons of glass. Of the 1 ton, roughly half is evaporated to provide cooling, the rest forms a wastewater stream. Most factories use water containing an emulsified oil to cool and lubricate the gob-cutting shear blades. This oil-laden water mixes with the water outflow stream, thus polluting it. Factories usually have some kind of water processing equipment that removes this emulsified oil to various degrees of effectiveness. Nitrogen oxides are a natural product of the burning of gas and air and are produced in large quantities by gas-fired furnaces. Some factories in cities with particular air pollution problems will mitigate this by using liquid oxygen. However, the logic of this, given the cost and carbon of 1. Not using regenerators, and 2. Having to liquefy and transport oxygen, is highly questionable. Sulfur oxides are produced as a result of the glass melting process. Manipulating the batch formula can effect some limited mitigation of this. Alternatively, exhaust plume scrubbing can be used. The raw materials for glass making are all dusty material and are delivered either as a powder or as a fine-grained material. Systems for controlling dusty materials tend to be difficult to maintain, and given the large amounts of material moved each day, only a small amount has to escape for there to be a dust problem. Colored, broken or waste glass is also moved about in a glass factory and tends to produce fine glass particles when shoveled or broken.